I don't know whether I will be able to answer the question that was asked yesterday. In fact, the reason why we're here is that we have so many questions that we need to put our effort together to use them, our information and answer some of the immediate questions. But my talk is going to be focused, as Dave mentioned, mostly on what have we done in terms of generating those first 25 scenarios. And of course, as everybody knows, this is just the start. And that doesn't mean that those 25 scenarios are already covering all the possibilities of the rupture realizations in the Hayward fault for a future earthquake. So I want to emphasize here that this is a team effort. We meet quite often, and it has been fun working together because it's a very mixed team. And I don't want to forget also acknowledging the work that collaboration with Rob Graves, who have been very nice to me when I ask questions, and he answered those very quickly. And so I really appreciate that, and I think we'll keep this collaboration in the future. So the outline is just a general information about the fault. I would like to touch base a little bit about what has been done in the past, because I think there's a lot of history behind what we're doing regarding simulation earthquakes in the Bay Area. I will just talk a little bit about the realizations and how we vary those parameters. And at the end, I still want to talk a little bit about the quality of the simulations that we're getting out of this very important simulation platform in applying it for actually past earthquakes, not just for simulations. And we'll see some results that are probably interesting, not only for people that are focused on just the science, but also application. So this is kind of becoming a very familiar figure, but I like because it just shows that the first phase of this platform includes the source and wave propagation. And as you heard many times today, we're using Graves and Pitarka rupture generator. And as Rob explained yesterday, this is a science-based rupture model. So we expect the rupture model to be evolving in the future. And Rob just showed a fresh development for that rupture. All my simulations that I will show here are based on the current version, not the future one that Rob talked, but I will touch base a little bit about the differences between them. What I want to mention is that this rupture model uses a hybrid steep distribution, so that means that there are ruptures that have just a stochastic variability, but there are ruptures that have some deterministic feature. And there is a depth dependency of the parameterization of the rupture, which I think is very important. And what is also important for this project is that, as they mentioned, we're trying to make the IOs very fast. And when we go to very high frequencies or very large fault areas, we are finding that the original SRF format of this rupture model that everybody now is using, and it started from SCAC and original work done by Rob, it's a kind of slow process. So we have now a converter from the SRF to HDF5 SRF, and that has helped a lot, and maybe Ojun will talk a little bit about. And then the SW4, we have been using mostly GPU based, but also we have version and CPU versions. And in fact, some of the simulations that we have been doing at Livermore are also based on CPU platforms. What makes this project very successful is that we have this impressive computation power, because it's a combination between different platforms that we have been using from several institutions in the country, and that has been really very helpful, not only producing ground motion, but also making the science that is at the base of that, and that has been very helpful. So I think many people are familiar with the active faults in San Francisco Bay Area. I just wanted to show this map. And why we are interested in the Hayward fault. So first of all, I I was impressed by the fact that, which I didn't know 10 years ago, that there is a 72% probability that a magnitude 6.7 or greater will occur in this region within maybe 40 years, 20 years. Also, that is a study that USGS has done a few years ago, maybe 10 years ago, that there is also a 33 probability of magnitude 6.7 on Hayward fault in the next 20 or 30 years. And that's something of concern because as people also mentioned, that this fault crosses across very populated area and maybe a very important infrastructure. And the problem is that we don't have a lot of earthquakes which we could use of this size, that we could use to kind of validate and also evolve our knowledge about what could happen for this magnitude earthquakes. For reason, because historically there have been very few of them, and the last one was 155 years ago, and it created some damage, but that's not something that we can use for calibration. And I think what we have right now is computation power and really good quality velocity model, as we mentioned, that could kind of help us in evolving our investigation about these earthquakes. So a little bit of history. There was a lot of effort about, well, here I start with R.D. Rogers, which is the recent one, who tried to, and the team that was behind this study, who tried to initially start using broadband deterministic ground motion simulations in broadband platform, and he did some analysis of ground motion in the Bay Area using a magnitude 6.5 earthquake, but at that time the first study was done up to 2.5 hertz, and then we pushed the simulation frequency range up to 10 hertz for a magnitude 7 earthquake using a VS mean 500 meters per second. So these studies help us to kind of explore what needs to be done and what can be we're losing if we don't use enough resolution in the rupture model and also in the velocity model. And one of the conclusions was that if we try to use only 500 meters per second VS mean, which is kind of typical in many areas now that we do simulations, and the reason why is that we want to save some computation time, is that you will miss a lot in terms of high frequency content of the signal, but also amplitude. And that was one of the conclusions of this paper. The other one was that if you try to use, let's say, empirical site corrections, they may not work very well in certain areas. And the reason why is that the ground motion models that use those empirical corrections are probably using very limited data for this kind of magnitude. But at the end, what these simulations that Arden did kind of created a background that we should really be able to do some work in terms of engineering applications. And then there's an important set of papers, I just picked up two of them from Brett Eggert group, who tried to actually model ground motion 10 years ago, or even more, 12 years ago, and Rob is one of the co-authors of those runs. They, at that time, they used deterministic approach up to 1 hertz, and then they completed the seismic ground with the stochastic approach up to 10 hertz. So those are really very good simulations because we did learn a lot about what you expect in terms of ground motion variability due to variability into the rupture model. But we also learned a lot about one of the unknown that we have for this fault, which is the creeping segment of the fault. So what was found that depending on whether you use creep on the Hayward fault, especially in the southern part of the fault, you may get lower slip during the rupture, and as a result, you may get a smaller magnitude and lower ground motion. That's what these plots show. And of course, there is a lot of questions about how to model the fault creep and whether it is extremely important for our future simulations. But anyways, I think what I like about this work is that there is some constraints that were learned about how to how to cover the parameterization of the future earthquakes, and they do have some conclusions about that. And so they found that the ground motion is very sensitive to the rupture area. I think this is kind of known, but it's nice to have examples about that. The hypocenter is one of them, and I'm going to talk a little bit about this. And the slip distribution also is very important. Well, they found that there is a weak sensitivity to rise time and the rupture speed. I think rupture speed is probably a parameter that is still not very well known. And I think the simulations can really help about that, because I do believe that super shear rupture or local super shear rupture could be something that needs to be included in our model. And then they talk about the fold creep. The other thing that I really would like to mention is work that Ruth Harris has done over the years, and there is a paper, a very nice paper that she wrote in 2016 about the uncertainties in simulation of earthquakes in creeping faults. And the reason why I mention that is that we talk about Hayward fault. And I'm quoting her because I think it's important. It kind of goes in my personal feeling that, and maybe some people here may not agree completely with that, but this is based on observations of earthquakes that are smaller than magnitude 6.7 on creeping fault. And she says, the analysis of strong ground shaking observations from magnitude 6.7 creeping fault earthquake show that in California show that the range of recorded peak ground motion is similar to the range of recorded peak shaking produced by earthquakes of the same magnitude that have occurred on local faults. And on the same line, similarly, the fault surface area that rupture appear to be neither consistently bigger or nor consistently smaller than those for equivalent magnitude earthquakes on log faults. So that means that, yes, the fault creeping is something that we need to consider in our rupture models, but it's not something that is well constrained. So we need more rupture dynamic modeling to actually understand what will be the best way to parameterize it, and also what would be the best way to represent it in its effect in strong ground motion simulations. So what I think the recommendation that we got from past work on this earthquake is that the earthquakes may nucleate at the boundaries between creeping and the log parts of the fault. That is something that we may consider for Hayward fault. And there is a low probability of large shallow slip where the fault is creeping. And then, we also have to acknowledge that regardless of the fact that the fault is creeping, we still have the potential that in a near future, in a future earthquake, there are still slip patches in that part of the fault that may generate high frequencies ground motion. And that's what we are after. And so that means that in the future model, even though that segment may not generate a large slip patch, it still may generate high frequencies. And as Ruth mentioned, that could be the case because that's what is observed. So I have a slide that I think Rob produced that years ago, but I think the science has not changed a lot except for details. But what I like about that is that it just lined down a little bit how this model was developed. We start with the K-square model that Martin Mai presented in his talk. And then we use the slip distribution to actually come up with a range of kinematic rupture representation that are related to the slip distribution. And of course, in order to model high frequencies, we have small scale variation, including the rake angle. We also vary the rupture time, the rupture velocity, and that is also based on dynamic rupture modeling for near surface ruptures. And we did find out, based on dynamic rupture modeling and feeding recorded data, we found out that there is a high possibility that the top part of the fault contributes to only long periods, not high frequencies. And that is enhanced also in the new model that Rob is proposing. And so how this energy is released in time is controlled by the source function. And that there is a lot of people that worked, especially Elisa Tinti, Massimo Coco in Italy, and Rob here, and a lot of people in the United States, including Ruth, is that we can represent that by a simple source function that has both the high frequency and low frequency part contribution coming from the source. But the key part here is that, and that's the work that we did with Rob and other people in Japan, is that it has to be variable. The shape has to be variable, and that is based on constraint-based or rupture dynamic. And that's what this model is about. So it's a combination of constraints coming from rupture dynamics, but also past earthquakes. Like, let's say, we don't know what's the rise time, the average rise time for an earthquake. And then Paul Somerville has some correlation that I think we use it, but it depends on earthquake. And of course, we made it variable along the fault. But these are some of the empirical ratios that we use in the code. Now, going back to the subject of this talk, so as Dave mentioned, we have already calculated synthetic seismograms for 25 scenario earthquakes on Hayward Fault, and they're going to be pretty soon available for people to use. We have been looking at those scenarios a lot, and the beauty of our project is that us seismologists can get feedback from the engineers. So we don't look at just time histories. We look at a lot of things, including response of the buildings and how the, let's say, the engineering characteristic of a ground motion change based on the parameterization. So we start now with a structure that has fixed rupture parameters, and then in the near future they're going to be varied. And I think yesterday we talked about how to make that database kind of inclusive of parameterization. But I want to mention here that even though we have to use some kind of power distribution for these parameters, I think for the time being, since we don't have the luxury of generating 1,000 ruptures, we should be kind of focused more on, let's say, the median value of these parameters, or something that has already been observed and we feel strong about it. And then using simulation, we can allow ourselves to kind of go to the extreme cases. So we start with the fault length, with the geometry. By the way, I want to mention that although R.D. Rogers tested the idea of this fault deeping somewhere toward the east, I think there is a consensus among geologists that this is a vertical fault. But we already know that depending on the deep angle, you may get ground motion on the hanging wall that are maybe higher. But in our simulations, at least for the moment being, this is the parameter that is going to be fixed in the future. We do have now scenarios among those where we drop the subfault dimension from 50 meters to 30 meters. And I just want to warn anybody that these simulations are accurate up to 50 hertz, up to 5 hertz, sorry. But we intend in the future to provide scenarios for specific earthquakes up to 10 hertz. And of course, as Rob mentioned the other day, the fault dimensions are going to be much smaller than that. So in this rupture scenarios, we centered our objective into the effect of the rupture initiation. So we have a balanced set of 25 scenarios with 5 hypocenters, and in which each of the 5 hypocenter, we slightly vary the slip distribution and maybe a little bit of rupture velocity. And the range of the rupture velocity that we used among each subgroup of 5 scenarios goes to 0.65 VS to 0.83 VS. And the reason why we have such a range of rupture velocities, even though in one of the talks, I think there was a concern that maybe the ground motion is not very sensitive to rupture velocity. I still believe that we can learn a lot from simulations, and the simulations do show that especially the rupture directivity effect, depending on the geology, does correlate with the rupture velocity, and I think we will keep that range broad as it is right now. But then, given the fact that we would like to quickly increase that database, and in fact, now we have already 40 rupture generated, and we're running those simulations as we speak, we are going to move the fault location. I don't think this is just an ideal location, but it's probably good enough to capture some of the effect of that fault in the Bay Area. I think there are a lot of people that think that this fault may extend even north, and I think that's probably something that we need to consider. The slip distribution is one important parameter that, and I'll show something about that. The slip patches, the hypocenter depth, the rupture velocity, peak slip rate is also something that the way that Rob designed the rupture generator, we, with our model, can control really nicely the roughness of the peak slip rate, which I already know is the main contributor of the high frequency ground motion. And the rupture generator has this capability of having a rough geometry. Here is just a quick illustration of the rupture kinematics. The red color shows the slip distribution, and the blue color will show how the peak slip rate change in front of the rupture, and you'll appreciate how much complex our rupture model is in terms of the local variation of the slip velocity and also rupture velocity. So you can see that it starts from what you get behind is the slip distribution, which is very variable, and then the blue is the peak slip rate, which is contributing to mainly the high frequency ground motion. So this is one of the realization. Now, just to give you a flavor how the rupture models will look like, overall these are the 5 hypocenters starting from the north to south. We do have a strong variation of the slip. Some of the slip large areas are shallow, some are deep, and of course this is part of the stochastic scheme that we can kind of use several realization to capture all these scenarios. But what I want to point out here is that if you look at the 3 panels, the top show the slip distribution, the middle show the rise time. You can see that because of the recent development that we had in our rupture generator, we do get a very strong dependency of the rise time, starting from longer to shorter with depth, and also we get a very high variation of the peak slip rate that, like I said, is also controlled by the roughness of that we want to put in those models. The other case would be how we generate different slip models, and I think most of them now have a stochastic variability, but I'd like to point out that we have now a lot of scenarios where we put a slip patch, and I think this is very important, and some of the speakers, maybe Floriana will show some of the results, that having a slip patch is very important to actually produce the expected ground motion variability locally, but also rupture directivity effect. And this kind of version of the code is like a substitute of the newest version. Rob shows that you may put now a shallow slip patch. But I think this rupture model, I'll show for the Loma Prieta earthquake, works extremely well. And I think it should be part of the parameterization. And then, as I mentioned, we move the rupture velocity. So I want to talk a little bit, I have only maybe a couple of minutes, about how we will build confidence in our simulations. So we know that everything here is based on science and experience and empirical, but at the end, as Camilo showed, we will build confidence just by comparing with data. And unfortunately, in the Bay Area, we do not have a lot of earthquakes. We have small ones, and so far, they have shown that our current velocity model, GS model, works relatively well. So we wanted to see, okay, now we're moving to very large rupture areas. We're lucky that we have data from an earthquake that happened not far away in time in the Bay Area, which is Loma Prieta earthquake. And as you can see, in the central map, it was recorded by at least 30 stations. That's a good number because they have a really nice distribution around the Bay Area. So it will be nice to see how well, first of all, our rupture generator works, and second, how well the velocity model that we talked about today, GS model, works not only at long period but also at the high frequencies. And this is a real earthquake. So we used what I call a GP rupture model that has actually two patches, and you see that those patches are a little bit deep because that's what was obtained from past inversion, long period inversion of strong ground motion. So there is the model that was proposed at Dave Wall that it was dominated by these two patches. So this is the only deterministic part in this model, so we have to use something that we know. But the other part is, I built a rupture model that has some stochastic variability, and I tried only one scenario. And so we modeled ground motion at 30 stations, and we tried to also understand whether this model works very well, including topography. And as you can see, on average, the bias is almost zero all the way to 5 hertz. This is something that we think that the reason why we get this kind of good match with data without playing with 100 rupture scenarios is that the velocity model, I think, as Camilo mentioned, it's working okay. I mean, we have a good model. We just need to improve it at certain areas, but on average, is a model that works very well. Second, what we want to do is, do we need the topography in our simulations? Is that important for future simulation? And the reason why we're asking this question is that there's no doubt that the topography has effect, even in this frequency range. But the problem is that the topography makes the simulation very expensive. It's almost a factor of 2 or 3. So is it worth it? So what I wanted to see is, okay, let's remove the topography. Of course, there's a couple of ways to remove topography. We use the one that we used in ESA before, so we assume that we have a flat topography. And as you can see, when the bias goes negative, that means that ground motion, the ground motion, simulated ground motion, has a lower amplitude. So immediately you can see that by removing topography, you kind of remove the effect of topography, but it's not a strong effect. It's kind of minor, and it's beyond, let's say, 3 to 4 hertz. So what I think is that maybe in the future, depending on the objective of the simulations, we may remove the topography and focus on some other parts of the model. And just for your illustration, I show the comparison in Fourier amplitude spectra. I have another poster for this earthquake. If you want to check, I have there a lot of waveforms that you can appreciate how well this velocity model works for the Bay Area. And just to give you an idea why we need to use GPUs, I put a CPU run for this. I had 2 runs, one is GPU with one with a CPU at Livermore, and you can see that we need 36 hours for 5 hertz simulations with a minimum VS of 250 meters per second. So I think the GPU is the future, and we're lucky that we have these capabilities that we can exercise our schemes. And I think I'll close here.